Good morning. In today's class, we will look at physical metallurgy of metal joining. Now, under this, these are the topics we are going to look at. We will look at common methods of joining. Although there are several methods of joining, we will primarily concentrate on welding. We will look at the bonding mechanism, look at the structural changes that take place during the process of joining, effect of processing parameters, how the structures get affected in the heat affected zone. We will also look at properties of joints and effect of service exposure, and many of these we will be talking about with few examples. Now, the common methods of joining, these are listed here. Rivet or nuts and bolts, here the main joining force is by friction. Two parts are held by friction, and the force, the normal force is applied either by rivet or nuts and bolt. Now, soldering, brazing and welding, here between the two joining parts we apply a molten metal. Now, here soldering, the molten that melting point of the molten, that metal that lies in the interface is very low, it is a low melting metal. In the case of a brazing, we do use a little higher melting point metal, but it is definitely much lower than the melting point of the metal that we are joining. Now, in welding, that the melting point of the metal is close to that of the part that is being welded, and in fact, a part of the a small portion of the parts which are joined, they also melt to provide better bonding. And another extreme way of bonding is adhesive. Here one uses synthetic polymer, but primarily we will look at the structural changes, particularly that takes place during welding. Now, brazing and soldering, here the parts in this particular case we just mentioned that parts to be joined, they do not melt. That is, the temperature of the interface is higher. Temperature of this interface temperature of this interface could be we will see, we will talk about is what should be the temperature of the interface with respect to the melting point of the filler. Now, to understand this, it is quite important that role of that solid liquid interface is quite important. Suppose this is the solid layer on which if you put a drop of molten metal. Now, depending on the surface tensions, the respective surface tensions, this is the solid vapor surface tension, this is the solid liquid surface interface energy, and this is the liquid vapor interface energy. And in fact, depending on their respective magnitudes, this angle at which that wetting angle is actually a function of the magnitudes of these surface energies, and which is listed over here. This is the expression that it is just simple balance of force. If you balance the force along this axis, then this is the x component of L v, that gamma L v cos theta, and they must be equal, and therefore, this wetting angle is a function of this surface tension ratios, the difference in the surface tension solid vapor minus solid liquid over gamma liquid vapor. Now, if this is low, that means theta is nearly equal to 0, then it has a good wettability, and in fact, for good joining where what we need is a thin layer of molten metal between the two mating surfaces. So, therefore, it must be wettable, whereas this is an extreme case here, this is a non-wetting liquid, and for good joints we need wettability, and apart from the wettability we need smooth clean surface, and also the interface temperature should at least be equal or greater than melting point of the filler, and this will help avoid dry joint. And a quick look, it is quite interesting to look at we will look at the magnitudes of the relative magnitudes of these surface energy. Now, in case of a welding, in case of a welding, the main difference in welding is this is the molten pool of metal, and the metal that is solid and liquid, they have nearly same composition. This has same composition. So, therefore, it is very likely that gamma liquid solid, this will be very low. And so, therefore, if you look at the expression for that cos theta, which is gamma S V minus gamma solid liquid over gamma liquid vapor. Now, what we know, say this solid and liquid, they are nearly same. So, therefore, what we expect that this is low and gamma S V is nearly equal to gamma L V. So, therefore, this is nearly equal to 1. So, therefore, theta will approach 0. So, therefore, welding this is assured. So, whereas in other cases you have to select the metal that you join, you have to select a choice of that filler metal also is quite important there. In this case, you have to select such a metal so that it wets the surface. Now, this slide looks at gives the bonding mechanism. If it is a good wettable that filler metal, then this will spread easily along this, and once it solidifies, it forms a metallic bridge between the two parts. So, therefore, bonding is essentially metallic. In fact, even if it is a soldered joint, the melting point of the solder material is low, their diffusivity will be relatively higher, although and they can at the interface they can react with the metal, some form intermetallic compound, or it can diffuse through it that interface, and there will be a thin layer of diffusion layer, and which gives the bonding. But nevertheless, the welding where the filler metal is almost similar to this, and where part of this solid also melts. So, there definitely the bond is going to be much stronger, and in fact, if you look at the relative strength of the welding, brazing and soldering, this will be in this order. This will be the strongest, solder will be the weakest. Now, to understand the process of joining what happens, it is necessary to know some idea about the heat flow that takes place during the joining process, and we will primarily consider the process of welding. And in fact, the concept that we learn here can also be applied to other cases as well. And this is the famous, this primarily the metals, they are conductor. The heat flow that takes place through metal will be primarily by conduction, and this is the expression, general expression for heat transfer by conduction. So, these are T is the temperature, x, y, z, this is the coordinate, and in fact, this small t represents time, and alpha is thermal diffusivity, which is a function of thermal conductivity over density times specific heat. Now, normally, so this is the expression which is valid when the source is stationary. Say suppose we strike an arc, do not move. So, that is the time that this will give the temperature distribution, how it will change with time around that heat source. Now, but in real welding there will be a speed, that heat source will be moving, and let us say that heat source moves with velocity v. Now, in that case it is quite possible, I mean quite easy to visualize what will be the temperature profile around the heat source. We consider 3 hypothetical cases. Say it is quite possible to I mean from our physical concept it is possible to visualize what will the temperature profile look like around the source. Suppose we have a point source, suddenly a hypothetical case. So, with suddenly within a solid at a certain point we heat it to a very high temperature. Never mind what is the method of heating, this is an hypothetical case, and in that case the conduction heat will flow by conduction in all possible directions, and conductivity will assume does not depend on direction, it is same in all direction, the thermal diffusivity is same in all directions. In that case obviously the temperature contour will be represented by a set of spherical surfaces, they will be concentric spherical surfaces. And in fact, and we extend the same thing if we assume the source to be a line source. In that case the contour, by applying the same logic, heat will flow in all directions on these surfaces. So, in fact, in this particular case the line source, the surfaces will be a cylindrical surface, the constant temperature surfaces will be cylindrical surface. Similarly, we can think about a planar source. If we have a planar source like this, in that case these contours will be just planar surface one after the other. But this temperature will therefore vary from this source heat source and the distance with respect to the heat source, and this is at any instant the temperature will be a function of the distance. Temperature at a particular point will depend on the distance from the source, and this will be something like this. Similarly, at any point the temperature will also go up, because we are just heating it and just withdrawing the source. So, at a particular point the temperature will go up, reach a maximum, and thereafter it will go down exponentially or something like this, it will go down something like this. So, in general what we can say, the temperature at a point will be a function of several factors. It will be the material parameter, thermal diffusivity, distance from the heat source, the time, and the heat that you have put in. And how do you find out the heat that you put in? So, this will be, say suppose in case of a welding, we can usually, if it is an arc welding, we can know the power that we put in. That power that we will put in will be product of voltage times ampere, and the time for which we apply it times time. But this is the power we put in, but the material may not absorb whole of it, and we can say that efficiency of arc welding is usually, there is an efficiency factor eta. So, 0.7 is a rough efficiency of arc welding. So, in that way we can get some estimate of Q, and let us see how do we use these concepts. Now, in welding the source does not remain stationary, it moves. So, if the source is stationary, suppose on this surface here we have suddenly raised the temperature. Thereafter, by applying the same logic, if we try and plot the temperature contour on the surface, it will be a set of concentric circle, and the center of these circle is the stationary heat source. Now, suppose if we continue to move it. So, if you move it, then this will get distorted, say something like this. In fact, that equation it is possible to show easily if this velocity is v for a quasi stationary state at a particular time. Say if we want to find out the temperature contour, we can take it to be a quasi stationary, ignore the time part. So, this is a velocity term comes over here, and physically what we can say that this source we are pulling it like this. So, heat source moves closer to these surfaces. So, therefore, they will be at a higher temperature. So, here it gets distorted like an elliptical, this kind of a distorted circle you can say, and then it is a distorted ellipse, and in fact, here the contours are closer, means here the gradient is high, here this side the gradient is low, and if we increase the velocity it will get again further elongated like this. It is possible to obtain some solutions under certain boundary conditions, like if we assume a point source, and usually point source represents multi-pass welding of thick plate. We will little while see why. Then a line source will represent a single pass welding of thin sheet, and these expressions, if you solve these equations and in r theta coordinate, say in this distance cylindrical coordinate, is possible to solve, and this is the nature of solution that you expect for thick plate. This is the expression. Q is the heat input, V is the velocity, lambda is conductivity, alpha is the thermal diffusivity, R is the distance from the heat source at a particular instant, and T 0 is the initial temperature of the plate you are joining, and these equations are valid outside the fusion zone. And schematically, that heat transfer is shown here for two cases. Thick plate. Now, thick plate, imagine here this is the molten pool. So, this is the molten pool, and surrounding somewhere a thin layer gets melted and they get mixed up here. So, very thin layer over here where we will get will melt along with and get mixed up with the weld pool, and here the heat can flow in all direction through the thickness direction, in all directions it will move. Whereas, so if you go back to the previous, what you see, that point source, this was more or less it is moving in all possible directions beneath that beneath the arc. So, here this represents a point source, whereas in the other case, if it is a thin plate, then this is the molten pool, and it is the molten pool, and the heat is flowing in two directions only. So, we will just look at this here. So, here this is the molten pool, this is the molten pool. In fact, this will be slightly raised. So, here also this is the molten pool. A thin layer beneath this solid will also melt, and in this particular case, beyond this fusion zone, heat can flow in all possible directions. So, we can visualize something like this. This we approximate as a point source with respect to the thickness of the plate, and heat is flowing through all possible directions in the 3D. Whereas, in this particular case, this is the thin fusion layer and this is the molten pool, and the heat is flowing in all possible directions. So, here contours will look like this. Temperature contours in this direction will look like this. Here temperature contours will look like this. And now, the solid pool that welding that solidification in that weld metal is also quite important. This will depend on the volume of the weld pool. We can always assume usually this is very small, and there will be a turbulence in the melt, helps good mixing. Normally, we have seen in that alloy solidification mixing is quite important, and in fact, if that mixing does not take place properly, and if say in the liquid the mixing can take place through diffusion, which will always take place, along with that convection or because of some stirring force, sometime arc applies some force. So, there will be some a kind of agitation and circulation. So, that helps in a good mix up and it distributes the impurities. So, it is quite important. The turbulence in the weld pool is quite important in getting a good weld pool structure. It will also depend on the composition of the mold. So, that is the metal that which is being joined, and usually metals we use similar metal as filler metal. So, they have some similar characteristics. There is also the solidification in this case is taking place under a high temperature gradient, because the mold is made up of metallic which has good conductivity, and possibly this may be in many cases at room temperature. So, the molten temperature is 1500 or 1550 degree centigrade to room temperature. So, you can imagine within a short distance such a high gradient existing. So, this also affects the structure that you get in the solidified metal. Now, dilution is also an important factor. A part of this metal which melts and mixes with the metal weld pool, and this is also quite important in forming good bonding. And weld solidification is therefore, it is a dynamic process, and this physical metallurgy whatever we have learned does help us in understanding the evolution of structures in various zones in a welded component. Now, if you look at that weld pool geometry, what will be the geometry? We just seen that this will get distorted, the source is here and these lines here, these will be closer. So, this direction the gradient is very high. So, here this is the weld pool, and this side the gradient is very high and this side the gradient is less. And when this weld pool progresses, it is quite interesting to see what will be the distance between the contours. I is the distance between the temperature contours. So, this has, let us say this is this this is the liquidus surface. So, this is where that solidification starts, liquidus. So, this is where that solidification is about to begin. So, imagine this is the grain, this will grow, as this moves this will grow, and growth direction will always be perpendicular to the surface. So, that means which is shown over here, that this is the growth direction, that is r. And if this heat source is moving at a velocity v, and this is the angle between the perpendicular to this interface and velocity. So, the growth velocity of the crystal, that solidifying front, will be equal to v cos theta. So, higher maximum, see where theta is 0. So, this is the point the growth rate will be maximum, this is the point where growth rate will be minimum, because here theta is 90. So, this is r is 0, this point. So, now it is quite interesting, if you can see that this geometry of this weld pool will be a function of several factors. It will depend on velocity, it will depend on the size, it will depend on lambda, the conductivity, and if these are low, we will find that these grains which are growing, they grow, and then this sometimes this directions also growth will change, and this is the type of growth which will take place. They will all be inclined like this, the directions keeps on changing, and in fact, in this particular case segregation, if at all is taking place, will all be distributed. Whereas, if these are high, in that case this actually this is distorted like this. So, in this case this width is also very small, and also you will get this kind of a columnar cellular growth, and always you will find that impurities they get segregated here. So, all high energy welding processes. So, this is a problem. So, these all these segregations will be pushed to this center line of the weld, and they will be the source of weakness. So, these are the lines along which often the fracture takes place. So, weld metal, the structure will essentially be a cast structure, and the rate of crystal growth is maximum when theta equal to 0. So, that means these points. So, that is why always it is elongated like this, but if it is very fast, in that case these you get this kind of a cellular growth and you have segregations here, and therefore, this center line segregation is a source of weakness and is a cause for poor toughness. Now, if you look at weld pool structure little carefully, here the dilution plays an important role. It helps ensure good contact between base metal and weld through formation of a fusion zone. That means, a part of the metal, base metal also melts, it mixes with weld metal and solidifies. Now, temperature goes above, definitely this zone, the temperature goes above melting point, and if the temperature goes above melting point, just surrounding region the temperature will be so high that there is likely to be excessive grain growth close to the fusion line. And say suppose this is schematically shown, you have these excessively large grains, and when solidification starts, this is the same metal. So, this solidification orientation of the crystal solidify will actually be an extension of this crystal, and it will grow in this direction. Similarly, this may have another different directions of growth. So, finally, so this is how the growth will take place, and this type of growth where the base structure that this interface determines the orientation of the new that is the crystal that is forming will have exactly same orientation as this. So, if these grains are coarse, that initial solidified layer will also be coarse. So, this is quite critical important. So, therefore, all high energy processes where the temperature goes very high for a short duration, but since the temperature is very high, there will be such large grain growth, and initial solidification will always be through epitaxial growth. So, therefore, it is even in a fine grain structure, there is very likely that near the fusion zone you will have extremely coarse grains. And the nature of that weld metal will also depend on the gradient, thermal gradient, and also the nature of that interface structure. As we said that in the heat affected zone, since the temperature goes very high, you have coarse grain. So, here there is an epitaxial growth taking place. So, that means same crystal, this is the fusion zone boundary, here they start growing like this. And we have seen, if you looked under solidification, this is the kind of the solute builds up near that liquid, that interface, because the solid which solidifies first they are purer. So, here this has a lower concentration of solute, and here there is a mix up, and in fact, there will definitely be some mix up, but still there may be some concentration gradient in the liquid, and the nature of that solidification will depend on and that whether the front will be planar will depend on the gradient. If this temperature gradient is very high, and initially always here it is very high. So, there it will be planar, and when it is slightly deviates from planar, say something like this is the gradient, this is the concentration gradient, and this is the temperature gradient, and in this particular case this is slightly less than this gradient. Here there will be a cellular type of structure. So, you have all these impurities are pushed these parts, this is the part, the intensity, this material they are pushed like this, these impurities, and in case this gradient becomes even lower, say something like this, there will be substantial constitutional supercooling and leading to the formation of dendritic structure. And here in this interdendritic channel you will have segregations. So, this explains that we just seen how our knowledge on the solidification can be applied to understand the structure that develops in the weld metal. But the properties of a welded structure depends a lot on the zone that surrounds that weld metal, and this zone is known as heat affected zone. And let us see what changes take place in the heat affected zone. Now, we will look at this with reference to steel. So, you recollect that phase diagram, iron carbon phase diagram. This is the austenite, this is the liquid region, this is ferrite plus cementite structure. Say suppose most of the cases the steel that we will be welding will be low carbon or medium carbon. So, this is say suppose this is the composition of the steel. So, initially there will be this molten zone, and here the temperature in this portion it is liquid, and this is a schematic diagram of a weld joint. So, you can think of clearly different zones. So, you will be zone over here which is molten. So, above this, and next there will be a zone where it just melts, that base metal here part of it is partially fused. So, somewhere in this temperature region, and this is number 2, this is 1, this is 2, and there will be also a zone just after this which will be heated to these regions. So, this is zone 3, and there is another zone which is related here, which is a normal heat treatment region. So, this is the zone that is 4. There will be another zone which is heated in this zone. So, this is 5. We can think of another which is heated in this region which is 6, and then beneath these the temperature is so low where we do not expect any structural change. So, we can clearly think of such 7 zones in a welded joint, and which are listed here. So, this 7th zone is the unaltered zone. Now, what will happen? The weld metal we have just seen, this will have a cast structure, then partially melted zone, it will melt and again solidify. So, here it has partly melted. So, these are the zones which are will partially melted and remelted and resolidified zone. So, you will have a mixed type of structure. Then this is a region where many of the steel you have like alumina, these types of particles in steels, inclusions, titanium nitride, vanadium nitride, carbides, and they block, they are very good, aluminum nitride, they are inhibit grain growth, but they also dissolve beyond a particular temperature, and when you heat it over here, these precipitates also dissolve. If they dissolve, then the grains will grow, there will be abnormal grain growth, grains will become very large. So, this is the excessive grain growth region, whereas this zone austenite will form, but that heating time is very short. This austenite may not be very homogeneous, this will be fine. So, when it again cools, this will have much finer structure, re-austenitized structure, there will also be quite fine structure. Then there will be a region where you have partially austenite. So, here you have austenite plus ferrite, and when it is cooled, this austenite may transform even to low transformation product, and sometime if the cooling rate is high, imagine say at this temperature zone, this has this much amount of carbon. So, when this is cooled, you may get some amount of martensite, or you can sometime depending on some alloy content, you can also get benitic structure. So, therefore, what you have in a welded steel, in a heat affected zone, a composite structure, and these are summarized over here. The transformation during cooling, we have just seen the different zones, they are heated to different temperatures, and this summarizes the different structures that you are likely to get in these 7 zones. So, weld metal, this is a cast structure, this is also the region which is also prone to solidification cracks. So, if sometime the cooling rate is fast, so it has not solidified, there is a thin, there is segregations, and then they can these are prone to solidification cracking. Similarly, if it is a partially melted zone, you also have a coarse grain structure, and these are the, here also you will have low melting liquid at the grain boundary, and they are prone to liquefaction cracking. Then you have excessive grain growth zone. So, this is this part. So, here you will have proeutectoid ferrite network. You can also have some amount of martensite, particularly if carbon equivalent is high. And this martensite, say in this particular case, since the grains are very coarse, so their hardenability will be higher and the cooling rate is high. So, therefore, the martensite formation is likely. So, this will have high hardness. Re-austenitized area, this will have fine grain of fine grain structure, ferrite consisting of ferrite and primarily perlite, and this zone is relatively wide, because this is the area where particularly in niobium vanadium containing steel, but bulk of the steel that are welded steels, they are microalloyed steel, they have some amount of niobium and vanadium added, and their nitrides and carbides, they are grain bound grain growth inhibitor, they do not allow the grains to grow. So, therefore, this particular zone, that re-austenitized zone, is quite large usually in this type of steel. Then we have a partially austenitized region, and here we have seen the structure that forms depend on the cooling rate, and we will talk about this temperature. What is this temperature? Delta T, the time it takes to cool through 800 to 500 degree centigrade. This is an important parameter often people talk about in welding. We will learn about it little later. So, here main structure will consist of ferrite and perlite. It can also form some kind of a plate martensite. We just explain, because that austenite is a high carbon austenite here. So, when it is cooled at a faster rate, it is likely that they can transform into martensite, and this martensite will be plate martensite. In certain grade of steel, you also get bainite. There is also a region where gets softened. Here the hardness can drop, can become lower than the hardness of the parent metal, and here the spheroidization process takes place. Carbides become spheroidized, and particularly the zone which is heated to 700 to 750 degree centigrade. This is the zone which is prone to this kind of softening process. And after that you have this unaltered zone, but this zone, since the temperature goes up, if there is a prior cold work or there are residual stresses, it is quite likely that these interstitial atoms can move to certain preferred sites, the dislocation sites, dislocations, and pin them, and this is called strain aging, which increases the strength and also decreases its toughness. It makes it brittle and prone to fracture. So, these are the likely the transformations which are possible in the heat affected zone. Now, how do you measure it, heat affected zone properties? The simplest measurement could be, if you take a section, the hardness measurement is quite easy. So, hardness profiles people have found out in the heat affected zone, and also you can develop microstructures in the different zone and look at the microstructure, and in fact, this has been done, and whatever has been said, that is how the 7 zones have been clearly identified in a welded structure. Now, if you look at this hardness profile and make a plot in the heat affected zone, you may find say hardness is usually reported in Vickers hardness number. Now, depending on the carbon content, say suppose if it is a medium carbon steel, say somewhere in the weld metal, we will forget, I mean let us look at that heat affected zone. We said that here there is a chance of martensite formation because the grains become very coarse. So, this is the heat affected zone just outside that weld metal where the metal has partially melted and you have a excessive grain growth. This is the region where grain size is very coarse and you have martensite. So, therefore, this is the region you have maximum hardness, and thereafter further you go away from the fusion zone, the hardness goes on decreasing, and there will be a region where there is no change. In certain cases around 700, 750, in certain depending on the initial structure there may be a dip observed also. This is because of spheroidizing, spheroidized structure. And if you also look at the microstructure, you will find this is the excessive grain growth area. Their grain size, and grain size is usually in steel measured in terms of that austenite, I mean ASTM grain size number. The austenite grain size is often represented as ASTM grain size number. We talked about in the lecture earlier, and lower the number, coarser is the grain. So, here this end the scale is this side. So, here the grain is coarse, and as you go away from the fusion zone the grains start becoming finer, and this is a zone here the grain size can become quite fine also, because this is a re-austenitized region where, and this re-austenitization it takes place for a very short time. So, the grains can become finer than the initial, and again it comes back, and this is that unaltered zone. This is the initial grain size. So, somewhere you also get a very fine structure. So, in short, this heat affected zone is a composite structure, and the zone which is more prone to failure is this is the region, and if this is hardness is very high, in that case the toughness will be low toughness, and coupled with it there is a gas related problem also. During welding process, if you are not able to protect the weld metal you are now from the surrounding gases, then these gases can get dissolved, and particularly among these gases hydrogen is quite damaging, and hydrogen diffusivity is quite high. If the welding electrodes are wet, they are not properly dried, if the slag layer on the weld pool is not protective enough, or the surrounding gas environment which is maintained is not protective enough, this hydrogen can diffuse into these regions, and if these hydrogens are present here, we may not see the crack immediately, but after you have welded and leave it for some time, and then you find there is a delayed cracking. Hydrogen relates to delayed cracking, and which is a major problem. So, you have to control that weld quality, that means welding electrode you have to bake them, and proper heat treatment is to be given, or depending on sometimes depending on the composition you may have to give prior heating or post weld heat treatment will be required. Particularly in cases, if you look up, if this hardness is very high, it is better to give a post weld heat treatment by which the structure will get tempered, and by that you bring down the hardness. Now, just now we looked at the transformation which takes place in the heat affected zone, and we also have talked about transformation diagram like CCT diagram, TTT diagram. Now, during welding, you do not have homogeneous structure through and through, you do not have uniform grain size. Certain places you have extremely high grain size, these regions may be very thin, but nevertheless to understand the structure. So, therefore, you need not the common normal transformation diagrams which are used to design heat treatment processes, but we need a different kind of diagram, and this diagram is known as the Weld CCT diagram, which are little different than the normal CCT diagram one uses in heat treatment. And one example schematic diagram is shown over here, Weld CCT diagram. But here the transformation by and large for most steels, the range in which transformation takes place, the diffusion control transformation takes place is around 800 to 500. So, therefore, all welding literature terminology, this temperature, the time it takes to cool through 800 to 500 degree centigrade is taken as, you can say, as a measure of the cooling rate, and this helps us to relate this hardness or microstructure with properties. So, this particular parameter is quite important. A typical diagram is shown over here. Say suppose something is a cooling at a slow rate. So, here it has a large delta T, this delta T is large, whereas somewhere which cools fast, say something like this, in that case here that delta T, this is small, and you can clearly see that here there is a chance of martensite, some amount of martensite forming, whereas in this particular case these products ferrite and pearlite is quite high. So, that means this type of diagram helps us to convert the cooling rate into microstructure, and microstructure can then be related to hardness. So, higher austenizing temperature is actually used, and obviously there will be welded zone, there will be austenizing temperature as high as this, where there will be excessive grain growth. And this CCT diagram we know is a function of austenite grain size. So, therefore, to understand this we need some method of calculating the CCT diagram. In fact, this is an area of great interest for physical metallurgists. There are many simulation techniques because it will be extremely difficult to generate these experimentally. The volume of data that will be required will be enormous, and they can only be found out through simulations. But nevertheless, this indicator, this delta T 800 to 500 is an important indicator or parameter which connects cooling rate to microstructure and hardness. And in fact, one such plot is shown over here. If you plot hardness against this, depending on the carbon content of the steel, you will have different types of relationships. Say particularly low carbon, you get this type of relationships delta T. Higher carbon, you get higher hardness in that welded zone. So, high hardness is will always have poor ductility, poor toughness. So, these are the steels will be where you get high hardness, they are the difficult to weld. And in fact, one of the ways of knowing this is to know or is to define that carbon content that you have, that equivalent carbon content. And if we look at this, there are several such expressions available for equilibrium several such expressions are there, such empirical expressions which gives you carbon equivalent, and these are different alloy element, manganese, chromium, these are the common alloy elements which are added, and using this it is possible to find out carbon equivalent, and usually steels where carbon equivalent is high, they are difficult to weld, and you need prior heating, preheating, post heating, so that you can control the cooling rate. And in that case, but weldable grade, low carbon grades are easily weldable. Now, this concept can also be applied to other alloys also, which do not undergo that kind of transformation. Like steel is a very special type of alloy, where you have allotropic transformation, where with a higher cooling rate you get a very high hardness product. But there are cases, say suppose we look at what happens if we try and weld an age hardenable aluminum alloy, and which is pictorially shown over here. An age hardenable aluminum alloy, if you recollect, this will have a terminal solid solution kind of system. This is a typical phase diagram of an age hardenable aluminum alloy. This is liquid, this is alpha, and what you do age hardening alloy, you heat it to this region, quench and then age, and by aging you get higher hardness, but when you quench your hardness is low, it is soft. Under quench condition it is soft, when you age it becomes harder. So, now what happens if we weld this alloy? So, here also you have to heat beyond the melting point. So, here also you can think of several zones. Obviously, this will be the weld metal, this will be the partially, there will also be a partially molten zone. This helps in mixing and bond formations, and this is also quite important that the base metal also should melt. So, therefore, you need to have matching electrodes, and once so this is a second zone. Now, there will be a third zone, where the precipitate will dissolve. So, zone which is getting heated to these regions, although it is for a very short time, but it goes to a relatively high temperature. So, the precipitates can dissolve, whether partially or completely, there is a possibility they can dissolve depending on the heat input and that whole time that you are likely to have during that welding process. Now, so you have, and there will also be a region which are aged over age somewhere here, wherever the initial precipitates that are there, they can coarsen, and below you will have that original metal. So, here also you will have a composite structure starting from cast metal to cast metal through partially melted zone, then with a coarse precipitate, then some of the cases you can also have that extreme case that is very far from the fusion zone, you will have the weld metal. And here also it is possible to compare or predict the microstructure. For that you need to know the transformation diagram. Here also you will have, we have learnt about it, you have C-shaped diagram, transformation diagram, and on this is time temperature diagram, and this is the C-shape, that transformation, that precipitation begins. Now, here when you are heating, there is a heating time, this temperature goes here, which is much above this, and it can say the heat affected zone. So, here is possibly it has dissolved, you have a supersaturated, you have a solid solution and it is cooled fast, and depending on the cooling rate, if it is cooled very fast, you will get supersaturated structure where you will have lower hardness, and whereas in some region which passes through this, you will have some precipitate. So, if you look at the aging graph, you may get a plot, say something like this. There will be a drop in hardness, and some cases there can be a little increase in hardness also. Say suppose a part of zone which has formed as a supersaturated solid solution, and during that subsequent cooling they can get some amount of natural aging. So, therefore, its hardness can also go up here. So, this is the distance from the fusion zone. So, this is, so that means in short what we have learnt here, that in the case of a metal joining, particularly we looked at welding in great detail. You are applying a very high or intense heat source in a localized area. So, at that time, during the process, not only the temperature of that zone is goes up, surrounding region, because metal is conducting, surrounding region, the temperature also will go up. It will go above the melting point, above the critical transformation temperatures, and therefore, the final structure that we will get will depend on the cooling rate after welding. And so, in short, whatever we looked at is different types of welding processes, joining processes, but we looked at in all these cases there is a diffusion bonding which takes place. In welding, even the part of the metal also melts. So, bonding is much stronger. There will be structural changes in the heat affected zone, we talked about it, and there is a processing parameters, like some of the parameters we talked about apart from thermophysical parameter, it is the dimension of the job is also important. The preheating, that temperature of the job is also important. So, the speed at which you do that, velocity of the weld, that heat source also affects the structure. We talked about how it alters the shape, the temperature contours, and therefore, the structure of the solidified metal, and all these will affect properties. We looked at hardness profiles, and hardness have a direct correlation with toughness. Higher hardness means by and large you have lower toughness. So, that has to be avoided. In steels where you are getting a very high hardness in certain zone, you may have to give post weld heat treatment to make it soft, to improve its fracture toughness. And we looked at all these with respect to, so one is steel, a low carbon steel, a microalloyed steel we did look at, and also we talked about the welding of an age hardenable alloy. With this, we complete the lecture on metal joining and also the course on physical metallurgy. Thank you very much.